Generally speaking, first of all, I would like to thank to the organizers of this event, giving me opportunity to present novel green nuclear technology for development of novel energy sources. It is actually my name. My name is Dimiter Alexandrov. I'm professor at Lakehead University in Canada, and my contact information is provided below, like email. So I'm a researcher, and I'm head of semiconductor research laboratory. I established this laboratory more than 15 years ago at the Department for Electrical Engineering at Lakehead University. I have more than 30 years experience in field of semiconductor technology, semiconductor theory, and generally speaking, uh, the establishment of the laboratory was very successful. The equipment which we see behind me is the part of the lab. So I'm going to, as I mentioned, actually, it was my laboratory, research lab, intends to make research in field of semiconductors. However, we are going to see later today what was the reason additional research to be added to the research activities of the lab. First of all, however, I would like to point your attention about the problem. Generally speaking, existing forms of mass energy production either produce significant greenhouse gas emissions. You see now the chimneys here of a normal thermoelectric station using coal for burning of the coal for production of electricity. Or we also may have some kind of radioactive waste or even radioactivity if we use some fission plants. Also, we can use actually solar and wind for energy production, but both of them, they are not yet cost effective at scale. They don't, in fact, both of them, solar and wind farms, do not create direct emissions. The initial production of the equipment, the storage of the energy nearly reaches the same levels of fossil fuel based energy production. It is not the solution. So the another actually attempts, which normally comes from the last about at least 60 years of research and significant investments. It's actually thermonuclear fusion. A lot of thermonuclear fusion, you can see, let's say, some kind of attempts of thermonuclear fusion. It, as I mentioned, actually, it accommodates significant investments, billions of dollars. And they've spent in the years, they're actually, in fact, two different technologies which are developed. One of the technologies, tokamak technology, the other one is laser fusion facilities. But both of them, they don't give the desired outcomes in order actually novel energy sources to be developed. Even as you're going to see, the successful experiments in the ignition nuclear facilities in the Livermore, which were reported approximately 11 months ago, they don't provide the exact opportunity about the immediate development of the novel energy source. But in fact, actually, these achievements, they have significant step ahead. Now, the another actually, as I mentioned already, solar and wind energy generation, energy production, they're widely used today, but as I mentioned already, generally speaking, both of them, they depend on the weather, they depend on the time zone. So now, they cannot be considered to be too successful as they maybe look, maybe they have impression. Generally speaking, one of the problems is that the generated energy have to be stored somewhere, let's say in the corresponding battery or battery system, in order actually to be used at the time when the corresponding energy is not available, which in fact is not actually solution again. The other actually way we to use the nuclear fission technology and technologies. There are few technologies in the world at present. They are actually good technologies. They are actually clean and clean technology, and the production, the energy production in the fission technology is very effective. But unfortunately, this technology, all technologies, they are actually radioactive, and all of them, they produce radioactive waste. This is actually danger for the human health. Generally speaking, the another limitation here is the limited amount available regarding radioactive ores, which are in the world, which are required for the nuclear fission reaction, mainly uranium. And of course, actually, we know that there are actually some very severe accidents in the near past. All of us know about the accident in Chernobyl. And also, actually, you can see on the picture the nuclear disaster in Fukushima in Japan. It was actually recently. So, the solution is development of novel nuclear technology. The history about development of novel nuclear technology comes from, in fact, 1988, when actually the first attempt regarding development of low nuclear fusion reactions have made on the basis of electrolysis of heavy water. Heavy water means deuterium oxide. Now, the problem there is that the experiments were not replicable. And normally, the released energy is very symbolic, like the amount, and normally the released energy comes from long time. It means we have to devote hours, even days of these experiments in order to get temperature increase in range of maybe 10 degrees Celsius or 12 or 15, something like that, until today. Now, I'm going to mention that thanks God, I succeeded to perform successful cold nuclear fusion experiments. It is actually based on a gas-loaded system, and it was achieved by chance. Generally speaking, in the spring of 2017, I observed, I made another experiments, including involving deuterium, and the experiments were connected with the increase of the growth rate of nitride semiconductors. And during the experiments, I found that there is increase of the temperature, and there is release of helium gas. No radiation was detected during these initial experiments. After that, actually, these experiments were based on gas, including deuterium nitrogen gas mixture, as the percentage of the deuterium was about 4.5% of the total gas mixture. The resting part was nitrogen. After that, actually, however, I began the experiments based on pure interaction of pure deuterium gas with solids. Especially, I concentrate my attention on interaction deuterium gas with palladium, with molybdenum. And the major success I found to happen in interaction of this deuterium gas with a constant tan. It is actually metal alloy, copper nickel metal alloy, very cheap, and which is actually put in the chamber. It is heated. We are going to see shortly a video clip now. And the process about the ratio between the ratio between the output energy and the input energy is between 380% and 1,600%, even greater. At the time, in the experiments where the deuterium gas interacts with a metal specimen, as I mentioned, based on constant tan, at temperatures between 600 up to 950 degrees Celsius. The output of the reaction is excess heat and stable helium gases. No radiation or other danger substance was produced during the experiments. And the important thing is that actually the experiment remained unchanged, and I was able to succeed using the same specimen for other experiments. In fact, a limited number of experiments can be done with only one specimen. The experiments are replicable. And generally speaking, during the experiments, the temperature increases from initial temperature, let's say, the experiments. The increase of the temperature was with additional approximately 400 degrees Celsius for a short time, about 30 seconds after the beginning of the experiments. So now, I would appreciate if Atanas now put actually the video on the screen in the chamber. There is no plasma in the experiment, so a glow here, which appeared, comes from the increase of the temperature of the constant tan wire, which is coiled here, with in its interaction with the injected deuterium gas. You see here the glow. At certain point of the time, I'm going to tell you when, the deuterium gas will be, the injection of the deuterium gas will be stopped. Now, The released energy comes from the cold nuclear fusion reaction in the wire here. The glow comes because of the temperature of the wire. At a certain point of the time, we are going to see I think now, yes, now we have stopped the gas. You can see the significant brightness of the wire. The temperature actually was just about above 100 sorry, 1000 degrees Celsius. And the glow comes from, again, from the wire which interacts with the deuterium gas, but there is no deuterium gas anymore in the chamber. That's actually the temperature here. The glow decreases and the reaction decreases too. So now it was demonstration of cold nuclear fusion reaction in constant on wire. Let's continue now. So you observed actually the exactly cold nuclear fusion reaction. The picture of cold nuclear fusion reaction can be seen on the screen here. What are the main parameters and how can we compare this reaction, the experiments which used to be held at Lakehead University, it is on the first column, with the experiments of national ignition facilities in the Lawrence Livermore National Laboratory, which were announced for the first in the middle of September of 2022, and they have been repeated again in this summer again. So now, the ratio output power, input power at my lab, it was 3.9, 16, up to 16 and greater in our experiments. Here in California, this ratio was 1.54. Operational temperature of the active nuclear medium, which just actually you saw, was between 650 and 1200 degrees Celsius. In the another actually facilities in California was actually greater than 3 million. As fuel here, it was used deuterium gas. In fact, you saw in the video clip interaction of deuterium gas with the specimen. It is not a radioactive gas. Deuterium-tritium gas mixture was used in the experiments in California. Tritium is radioactive. Regarding the released radiation, no radiation was measured during the experiments, including gamma rays and neutrons. Here, in the facilities in California, there is no reported data. Radioactive waste, there is no radioactive waste in my experiments. Here, there is no reported data. Now, the time for development of the reactor prototype using the experiments which actually was achieved in my lab is up to 24 months. Here, it is a norm. So, what is in fact the difference between the experiments at my lab, which just actually you saw, and the previous experiments? As I mentioned already, it was done by chance. Initially, the experiments were not intended to take place. However, after it actually a significant energy released and helium, both of them were measured in the experiments. So it is one difference between the experiments at my lab and all other experiments before and even at present in other labs. The other actually thing is that the other specific feature is that the experiments in my lab normally give energy release, giving its maximum for 30 seconds after the beginning of the experiments. It means we don't have to work for somehow for experiments for actually long days or even hours duration of the experiments. And the another important feature is that the experiments are connected with helium release. And also the important feature is that no radioactivity was measured, including neutron release and gamma ray release. So, how it can be used? The estimated electricity production will be below 10 cents per megawatt hour, pertaining to the released energy. If the technology based on my discovery will be used. It could be used for clean power, the electric directed, which can be connected to the grid, which is actually low cost, clean energy versus the current methods. The hydrogen production and storage can be used in transportation. Hydrogen production, it means the nuclear plant based on this technology can be used as energy source for hydrogen production. Small enough can be deployed remotely anywhere. Hot fusion plants, if they ever work in the future, will be extremely large and expensive to build. Solar and wind also are very expensive by comparison. Stationary and mobile applications for ships, trucks, submarines, and even for other vehicles such as cars and trucks can be used. How about the cost? The type of the source we can get here is for single household energy source. The intention is the dimension of the single household not to be more than dimensions like a home fridge. The output power will be 10 kilowatts. The cost will be this amount, about 3.2 cents per kilowatt. And here is the comparison regarding actually the electrical power coming from the electrical grid or from the natural gas. If we design a reactor based on this technology, having power 1 megawatt, the cost will be less than 1 US cents per 1 kilowatt hour. And here we have actually the comparison with the cheaper, the cost regarding the electricity coming from the electrical grid or energy coming from the natural gas. Now, all of these costs here, if we, let's say, incorporate a very small source in a vehicle with having in a hybrid vehicle having output power 75 kilowatts, the cost per 100 kilometers will be 40 US cents. And it's actually the amounts which is less than gasoline. Now, these costs here are calculated on the basis of the deuterium, cost of deuterium gas for 10 years, maintenance for 10 years, and initial cost of the equipment. So you can see the difference in this way. The intentional development of 10 kilowatt reactor prototype, as I mentioned, actually the intention will be to have dimension like a home fridge using this novel nuclear technology. The startup phase is completed. There is a design of 10 kilowatt reactor. The patent is processing and start cooperation is established. Further development of the prototype requires establishment of consortium of companies, secure funding for prototype development, not too much, between 3 million and 4 million for development of the prototype, and in order to be built and to demonstrate the working prototype is between 18 to 24 months. After that, actually, after the second phase, we can go on the third phase for actually mass production of the corresponding reactors. The phases for developments of other energy sources, such as 1 megawatt and mobile source, are similar, but of course, actually, the required funds will be different. Thank you very much. It was my presentation. I will appreciate and I'm ready to answer on all of your questions.